Suppose an object travels with increasing speed along a straight path. The object's speed is recorded every 2 seconds. Here's a table of values showing the time from 0 to 10 seconds and the speed in feet per second. And if we plot these values, we get a graph that looks something like this. And so we want to find a lower estimate for the distance that the object traveled. So if we want a lower estimate, we know the speed is increasing throughout the 10 seconds. So the absolute minimum distance it could have traveled in the first 2 seconds can be determined by looking at 2 seconds times 10 feet per second. Remember, if we have a constant velocity, we can say the distance is velocity times time. And if we assume that the velocity is a constant 10 feet per second, that would be right here for 2 seconds, then this represents the distance that the object traveled in the first 2 seconds. That's the same thing as calculating the area of this rectangle right here. Now if we look at the next 2 seconds, for the lower estimate, we can assume that the object traveled at a constant 30.9 feet per second. That'd be the minimum it could have traveled in that 2 seconds. And that'd be the area of this rectangle. And then we have the next 2 seconds. So again, we have 40.6 times 2. And in this case, we have this rectangle. And then we would have 48.1 times 2. That's this rectangle. And then we have 54.4 times 2. And that's this rectangle. And if we add up all those areas of all those rectangles, we get 368 feet. And that's our lower estimate. For the upper estimate, let's look at the most the object could have traveled. So in the first 2 seconds, we know at the end of the interval it was traveling at 30.9 feet per second. So let's assume it was going 30.9 feet per second for that entire first 2 seconds. So in that case, this leads to an upper estimate of 30.9 feet per second times 2 seconds. And now we're looking at the area of this rectangle right here plus this added rectangle right here. Next, we have 40.6 times 2. So now that would be the next one over. And so we add in this little rectangle. And then we have 48.1 times 2. That adds in this little rectangle. Then we have 54.4 times 2, that adds in this rectangle. And finally, we have 60 times 2, and that adds in this little rectangle right here. And that gives us 468 feet for an upper estimate. Well, there's another way to think about this. Here's our lower estimate of 368 feet and our upper estimate of 468 feet. And we see the difference between them is 100 feet. Look at all of these shaded rectangles. Imagine stacking them one on top of the other. Well, if we look at the height, we get 50 feet per second. That's the difference between the largest measurement for the speed and the smallest measurement. And then down here, the width is 2 seconds because we have 2 seconds in between each time measurement. And then the area of this shaded part is 50 times 2, or 100, which also represents the difference between our two estimates. All right, now suppose we look at the same situation, except we're going to record the object's speed every second. So now we have twice as many values here. And if I were to plot them, I would get something like this. And we're going to again look at a lower and upper estimate. So first, a lower estimate. So we have 10 feet per second for the first second. That means I imagine that the object here during that first second is going a constant 10 feet per second. That's the lowest it could have possibly gone because we know that the object is traveling with increasing speed, so it couldn't have gone any less than 10 feet per second during that first second. That represents the area of this blue rectangle right here. And then we have 24 feet per second times 1 second. That's this rectangle. And then 30.9 feet per second times 1 second, that's this rectangle, and so on all the way to the end. I won't say them all out loud here because you get the idea. So we're adding up basically the areas of all of these rectangles. And when we do that, we get 397.2 feet. Okay, now let's look at our upper estimate. So now for the first second, I'm going to assume that the object traveled at a constant 24 feet per second. So in that case, I add in the area of this light blue rectangle right here. And so I'm going to do the same thing. I'm going to keep adding in areas of rectangles here to get our upper estimate. And once we do all of this, we end up getting 447.2 feet for the upper estimate. Okay, so for the lower estimate, we had 397.2 feet. For the upper estimate, we had 447.2 feet. The difference between the estimates is 50 feet. And again, we can imagine taking all of these rectangles here, stacking them up so that we get one giant rectangle here. And once again, the height of this rectangle is 50 feet per second. That's the largest speed measurement minus the smallest speed measurement. And now this time the width is 1 second. 50 times 1, that's 50. So that gives us 50 feet, which is the difference between the estimates. Now what if we recorded the object's speed every half of a second? So we would get a whole lot of values here, and if we were to plot them, we would get something that looks like this. And I'm not going to put in all of the rectangles here because I think you get the idea, but let's take a look at the difference between the estimates. When we were looking at measurements every 2 seconds, the difference between the estimates was 100 feet. When we looked at measurements every second, the difference between the estimates was 50 feet. So you might guess that if we look at the measurements every half a second, that the difference between the estimates should be 25 feet. Let's figure that out. So if we look at the difference between the largest and the smallest measurement, so that's 60 minus 10, this part right here, that's the difference between the largest and smallest measurements. And then we multiply that by the width, which in this case would be the time between each measurement, that's half a second. And if you multiply those things together, you do indeed get 25 feet.